Here we are. It's the physics video lecture. Physics 190 video lecture 11. This may be the last one, but we're in no hurry. I have all the material I want to talk about laid out in front of me, so today, possibly next time. So where were we? We have this great application, the damped driven oscillator, and we're solving it with Fourier integrals, and in order to do the Fourier integrals, we had to go into the complex plane and use the residue theorem. So what I'd like to do is get everything that's necessary for the problem up on these boards, and then I can just wave the ruler around at it and talk about it. So what we had here was the damped driven oscillator. And its differential equation, I'll just go straight to 2 time derivatives plus 2 gamma first derivative plus omega naught squared x equals, and then we had a f naught over m. We had a cosine. I'm going to write cosine driving frequency times t, and we needed a damping factor, a converging factor minus alpha t. So here alpha was greater than or equal to 0, and here alpha is greater than 0. Later on we can take the limit alpha goes to 0, no problem. And we're looking for positive times. Okay, so there's the problem. The definitions of these quantities are given previously, so no problem there. And the way we were going to solve this, now I'm going to write solution. There were a few intermediate steps without a doubt. Was this: x of t is equal to the integral x hat of omega e to the I omega t d omega. T goes from minus infinity to plus infinity. And we're ready to solve this integral because we have found x hat of omega. So when we take it into the complex plane, the x hat of omega that we found times e to the I omega t is that function, that complex function that we're going to extend into the complex plane. And our job was to find x hat of omega. We have it now. And this is part of that expression as well, multiplied by that. And when we go into the complex plane, we know that if we close the contour in the upper half plane, that we have convergence. So everything is by Jordan's lemma. So everything is fine. So let me go ahead and write what this x hat of omega times e to the I omega t looks like. And I had a couple of ways to express it. Yeah, I'm going to do this. So we've got minus f naught over 2 pi times I times m, m's mass, omega minus I alpha, and then I've got e to the I omega t right there. And in the denominator, I have these 4 poles. I'm going to write omega minus omega 1, omega minus omega 2, and omega minus omega 4. So we have 4 simple poles, first order poles. This shouldn't be bad. And I'll even put the definitions of the poles right here as well, then we'll kind of be complete. So I'm calling omega 1 this gamma plus, omega plus I alpha. Omega 2 is minus omega plus I alpha. Remember, the omega is the driving frequency. Now the omega 3 and 4, I'm going to put comma 4 equal to I gamma plus minus root omega naught squared minus gamma squared. So those are two poles here. The third, number 3, is with a plus sign, 4 is with a minus sign. If you want, you can write them out separately as well. I was just running out of room. Yeah, we have all of the ingredients. And we've been here before, but I just want to really make sure we discuss this thoroughly. Yeah, so let's look at our contour. First of all, let's look at these poles here. We've got the complex plane and omega plus I alpha. So anyway, I have omega and minus omega, uppercase, the driving frequency, and I have I alpha here. And so those two poles are right here. So this is omega 1 and this is omega 2 in the complex plane, you know, over and up I alpha. And then omega 3 and omega 4, I'm just going to have plus minus, so root omega naught squared minus gamma squared minus root omega naught squared minus gamma squared. And then we'll put the I gamma here so that we go over and up. And now we have those 4 poles. Yeah, those are the 4 poles. And I'll go ahead and even put omega 1, omega 2. Make up my mind. Those are going backwards. Here we go. So omega 1, omega 2, and then 3 and 4 are the plus and minus signs. So omega 3 and omega 4. So the contour, because we now extend this integral into the complex plane, minus infinity to plus infinity, so that's the limit of some r and minus r here. And when we close the contour like this, so our integral is around this contour. And in the limit as r goes to infinity, Jordan's lemma tells us that because this integrand vanishes as r goes to infinity, if this x hat of omega clearly vanishes, you know, 3 powers of omega, then this entire semicircular arc integral vanishes in that limit. R goes to plus or minus infinity. Yes, what else? So we're going to pick these off one by one. Now what we're therefore going to have, so x of t equals, I'm going to go ahead and write this, x hat of omega is I omega t d omega plus, and I like this symbol here, this arc r I omega t d omega. Yeah, this one is going to vanish as r goes to infinity. And the total integral, on the other hand, is going to be equal to 2 pi I sum of the residues of x hat of omega e to the I omega t. Some of those 4 residues, in fact, omega equals omega sub k equals 1 to 4. Okay. So we just have to get all 4 of those. And they're simple poles, so each time we evaluate one, and this is what I want to make sure everybody gets. For example, the residue for this thing at omega 1, we multiply by omega minus omega 1, which essentially just cancels the simple pole. and evaluate the remaining 3 at omega 1. So to get started here, and you guys do all 4 of them, 2 pi I minus f naught over 2 pi I m omega 1 minus omega e to the I omega 1 t, and this is going to cancel this minus omega, oh, back up here. Not so fast. Okay, so we have omega 1 minus omega. This is that recipe. We multiply the entire thing by omega 1 minus omega. So now we have once more we're doing omega minus omega 1, omega minus omega 1. Yeah, okay, sorry. And then we have omega minus I alpha e to the I omega t. So I'm just writing the entire thing down with this. I'm going to put this in some little red bracket or something. Omega minus omega 2, omega minus omega 3, omega minus omega 4. Okay, so what I've done is I've multiplied this part here by omega minus omega 1. So the rule is I multiply by the expression that eliminates the simple pole. So these 2 are gone. And now I'm evaluating this at, let's see here, evaluating what the rest. So I've eliminated the pole, evaluating the rest of this at omega equals omega 1. So now this is evaluated omega 1 minus I alpha e to the I omega 1 t, and omega 1 is this one right here. And then the product of these 3, right, this is the one that would have been a pole that vanished, so these just give these 3 complex numbers that you're multiplying with each other. And you do this 4 times. So plus, I can spare this part of the board here, plus 2 pi I times the next one, plus and so on. You do this 4 times, once for each of these poles here. So the next time you multiply by omega minus omega 2, well, you don't actually even have to do that multiplication. If you know the rule, you just strike it. Okay, you just strike it from the record, so to speak. Then you strike the omega minus omega 2, 3, and 4, and plug in these complex numbers. Of course, they're not going to be that simple. You may remember that the amplitudes in our damp-driven oscillator were pretty complicated, right? They had all the physics in there. So of course you're going to regain that. Okay, but we want to stand back, and once we recognize that process, we want to stand back and see what kind of physics we can understand on this. Okay, so this here, just to be sure, blocked off there. You do this sum all 4 times, and here I did it once. You're going to plug those numbers in. But we want to just see the actual physics. So, right, we continue this one down here. Okay. So that should be clear. The integral that we were looking for, this one right here, break it into this part and the upper arc. This one vanishes by Jordan's lemma, and the limit as r goes to infinity. And the entire thing, of course, is just 2 pi I on those 4 residues. Which, by the way, long before we had the residue theorem, when we had Cauchy's integral formula, we realized that we could actually do this with single poles. this just gives a good recipe for it. Now, let's talk about the physics of these poles again, because you see when you plug in this omega 1 and you see what it is, what are you obtaining? You're obtaining an e to the I capital omega t, and then I times I is negative, so you're obtaining an e to the I omega t minus alpha t. So, of course I don't have that much board left, but I'm going to block out a red square. You guys put this where it fits best. Here's what you're getting. You're getting e to the I omega t times e to the minus alpha t. And everything is going to be well behaved, so when you take that limit alpha goes to 0, you're left with e to the I omega t. So these poles dropping down to the real axis corresponds to the purely oscillatory term here, right? We're going to have corresponds to the purely oscillatory term, but we solved this thing generally, so you could say we have the solution for a damped driving force as well. But we want alpha to go to 0 at the very end. When you do the same move for omega sub 2, you're going to have the same e to the minus alpha t, but you're going to have e to the minus I capital omega t, and the sum of those two, of course, is a cosine. So as you go through with this process, you're going to pick off your purely oscillatory, and at t goes to infinity, since you let alpha go to 0, you're just left with your purely oscillatory term, okay? And all of the coefficients in front of it, that's that amplitude that we had last semester, you know, in which you can discover resonance and other things like that. So that's what these first two of this sum of 4 are going to give you roughly. Now, the second two, we're not setting, I wrote alpha here. This, of course, is gamma. I can correct that in real time. So yeah, the second two of these poles, omega 3 and omega 4, remember, you're just going to plug up these things in and get some eventually recognizable expressions, okay? Just numbers. So if we're looking at what's going to happen with the exponential, we're not setting gamma equal to 0, so these two poles give you damping. And we already see the stronger the, you know, if we send these poles up higher in the complex plane, that means stronger damping. If we drop them lower, it means weaker damping. So these poles and their locations contain all this physical information that if you're doing this a lot, you start to just know what the poles mean. So just, you know, having your function and the location of the poles, that tells you what the physics is. Okay? Because again, drop them down to the axis, purely oscillatory. So let's look at what we're going to get. If we plug in, say, omega 3 here, so e to the I times I gamma, that's e to the minus gamma t. Okay? And then we'll have plus minus I times this thing again, so it'll be e to the I gamma t. I've got room here. Well, I'll block off. This is for 1 and 2, and for 3 and 4. We're going to have right here, we're going to have, you know, the evaluation of all these products. Sure, got that in there. You've got rid of the pole. You're going to have e to the, I'm just going to write plus minus root, oh, there's an I in front, plus minus I root omega naught squared minus gamma squared t. Okay, you're going to have that, and that's just purely oscillatory, but both of these will be multiplied by e to the minus gamma t. So these two will really be the transient as t goes to infinity. Contributions of these two poles are going to vanish as t goes to infinity. Contribution of these first two, when you set alpha to 0, right, go on down to the axis, those are going to be your resultant-driven oscillation, and that's the one that we studied last semester. Okay, so it looks worse than it is, but of course there's plenty of room to make little algebraic errors, but you see where you're headed. You're going to have these two here, they're going to be your cosine, and these two here, those will be the sinusoidal ones that are damped as time goes to infinity. So these will be your 3 and 4, we have these, and these will be our transient terms. And yeah, the whole, make sure you write the whole thing out though. You leave yourself enough paper and you can start to pick off what's going on. And then you'll see in these limits as alpha goes to 0, the terms of t to the minus gamma t, you definitely want to put those off to the side because they are the ones that vanish as time goes on. Okay, good. So I can't really say any more than this. You have to dive in there and try it. I think we have a pretty thorough description of this. And definitely, graph these things out and ponder them, what they're doing here in the complex plane. Okay. Very important and common technique in physics is to go into the complex plane. Has been for a long time. So this example was a pretty substantial one. We had this damping we had to put in at the outset because it was a converging factor. But you put it in, do your calculation, then you find that you can set alpha equal to 0 with no harm done. So yeah, all these features I think you'll appreciate. Just take some time, write it all out, make sure nothing gets lost, and enjoy it. Good, so that's the one thing I had to say. And the next thing I want to do is set up a couple of more interesting integrations. I'll take them far enough so that we can definitely do them, and we'll make those the last homework problems. All of this, so this thing right here, done very thoroughly, and then these next two integrals will be the last problems in the semester. Homework problems, and I think we'll round things out pretty nicely. So I'm going to erase all of this, and we'll discuss a couple of more integrals. There's a whole world of integration techniques, and we're touching on a few, but they should really open up your eyes to the possibilities. So what I'll do is I'll formulate them as two problems, and then I'll just get started on them and give all kinds of pointers. So show that the integral from minus infinity to plus infinity x to the third sine of x. Is this what we're doing here? X to the third sine of x dx over x squared plus 1, the quantity squared. I'll even put the answer there right away. So I've got it all here. I'm just going to give you pointers. That is pi over 2e. Pi divided by 2 times e. Yeah, that's a great answer just because it has pi and e in it. Okay, so how do we want to tackle this thing? the way we're going to tackle it is to consider a couple of lessons here, but okay. We're going to consider the integral z cubed e to the I times z dz over z squared plus 1 to quantity squared. And we're going to consider it along the ordinary path that we usually take along, r minus r here, the complex plane, along this one, okay? Because it turns out there is going to be a pole at I. Here we have z plus I, z minus I, but it's squared. So we have, enclosed in this path is only one pole, but it's a second order pole. And we have a theorem, we have a recipe for dealing with those that I showed. So it's in your notes. It's that derivative version. So there are a couple of issues here. Along the real axis, this integral is just the imaginary part, okay? So I'm just going to put some notes. I give these a name. Let's call this integral equals I, and this here I prime. So I is equal to the imaginary part of the integral I prime as r goes to infinity, comma, because this upper arc here goes to 0 by Jordan as r goes to infinity. Jordan's lemma tells us this upper arc goes to 0 because we have z to the third over z to the fourth, so we have something that vanishes, and we know that this one can be approximated in the limit as equal to pi, the magnitude equal to pi. So Jordan's lemma, I'll do, by Jordan's lemma. So look up Jordan's lemma again. So that's not that bad. You're going to have one residue here, but it's a second order residue at plus I, right? Second order residue at z equals I. And you know that was the d dz of z minus I squared f of z, right? We had that theorem. To cancel out those residues. So, etc. So that was also the tip you had to use. So this isn't bad. It's the imaginary part. A lot of eyes here. The integral we're looking for is the imaginary part of this one here. I can even draw the path like that as r goes to infinity. But I'm saying it so you guys know the routine. Okay, so this one will be interesting. You'll have to make use of a couple things and then to whole of second order, get a nice result out. Now there are some pitfalls that I wanted to mention. Some mistakes that are easy to make. Suppose we had decided to say, okay, let's write it this way. Let's write z cubed, z squared plus 1 squared But then here we had written 1/2 e to the iz minus, I'm going to write this out. Let's write this out a little neater. Okay. Suppose we wrote I prime equals, I'll bring the 1/2 out in front, integral z cubed z e to the iz minus e to the minus iz dz over z squared plus 1 squared. Okay, suppose we had written that and we wanted to do the same contour. Looks like fine, that's the sign. We don't, instead of taking the imaginary part, we've got the entire sign here. That's the divided by 2. That's the sign of a z in the complex expression. However, this is not going to work because problem exclamation points problem. Problem is this: if you close the contour in the upper half plane, that's going to work for this one, but you're going to get divergence for this one here. So integral, let's just look at this one alone, e to the minus iz dz would diverge in the upper half plane. There's a technique for that though. The same discussion of Jordan's lemma would show us that we would have to close that contour in the lower half plane. Okay, so this one has to be closed in the lower half plane. So you could solve the problem by, it would be harder, by breaking this up into 2 integrals. This one you close in the upper half plane, this one you close in the lower half plane. In fact, it gets a minus sign because it's clockwise instead of counterclockwise, but there's a half there. When you add them all up, you'd get the same answer as before. So you can certainly do that. So this one must be closed. So the contour must be closed in the lower half plane. So we're not going to do it that way. Or, by the way, you can actually try that. I'm asking you to do this, but if you close this first half in the upper half plane, the second half in the lower half plane, and note the minus sign here and the minus sign from clockwise, you'll actually get the same answer as before. So it's about twice as much work, but it's a pitfall to be aware of, because if you were just to blithely do this, okay, close it in the upper half plane and not be aware of this guy, then you'd make a mistake and you wouldn't even notice it, okay? And by the way, that is because e to the I r e to the I theta minus I is going to, diverge in the upper half plane. Close in the lower half plane. Okay. So good. That's enough info. You didn't need to know this to solve the part above there, but this is just something you have to know. If you're ever dealing with this, you just don't automatically close things in the upper half plane. You have to make sure you're converging there. Okay, enough said about that. So that's a good problem. And let's see, we're going to wrap this up with one more really interesting integral. I think this really will wrap it up. What I'll do is after this I'll be in contact with you guys. We can do a Zoom meeting or something if we have any final questions and thoughts. So here's the last integration that's pretty interesting. Let's see. So this time we want to calculate, so show that the integral I have here, yeah, 0 to 2 pi d theta A, is it plus or minus? A plus cosine theta, yeah. All right, it's completely different now. We're not doing 0 to infinity. 0 to 2 pi, d theta A plus cosine theta equals pi over, this is a great problem here, equals 2 pi, unless I made a mistake, root a squared minus 1. So what we're looking at is a strictly greater than 1. So we're going to do this with complex techniques as well. This one is a pretty rich problem. So let's see. Here's what we do. I'll just get started and show you the way if we're going to prove that. So what we're going to do is let z be equal to e to the I theta, and then we know dz is equal to I e to the I theta d theta. So here's where we can express this all in terms of z instead of theta, and the upshot is that we'll turn this 0 to 2 pi into an integral around the unit circle in the complex plane. So I'll just continue the thought here. Then cosine of theta, which is 1/2 e to the I theta plus e to the minus I theta. And we express that in terms of z. We have a half z plus 1 over z equals 1/2 z squared plus 1 divided by z. And what about this dz here? We get d theta is equal to dz over I times z. So now we can use these substitutions. We can use these substitutions in this integral here, which we'll name I. I is equal to integral, we have dz over I times z, and then we have this a plus cos theta, a plus this entire thing right here, a plus 1/2 z squared plus 1 over z. And now we want to simplify this thing, but we can already say that it's around the unit circle. We want to simplify this, and it's going to simplify nicely because the common denominator here is going to cancel that z right there, and we're going to have 1 over a quadratic. Okay, I don't want to give the whole game away, but I do want to give some of it away. Let's see. Make it a little more room. See how far we take this. Yeah. We're going to put 2 divided by I dz 1 over z squared plus 2az plus 1, right? 2az plus 1, 2 over I. Yeah. Unit circle. And now I have to be a little more general. Don't want to give everything away. But yeah, this is the integral we want to do. And what we're going to find is, just by using the quadratic form, there are two roots of this. Remember, a is a positive real number greater than 1. So there are two roots of this, and only one of them is inside the unit circle. Okay. So let's write this: z squared plus 2az plus 1 quadratic formula is equal to z minus z sub 1, z minus z sub 2. One of those roots is in the unit circle, and that's the pole for which you can use the residue theorem. Okay. One root is inside the unit circle. And you know, here's your unit circle in the complex plane. And there's going to be one with a, so here's C, that's 1. And there's going to be, you know, one that's inside the unit circle somewhere and one that's outside, okay? In fact, I think it's over to the minus direction. But you guys can discover that. One root's inside the unit circle somewhere, depending upon the value of A, so you have to monkey around with that a bit. And then it's just the residue theorem, okay? So then this integral will end up being 2 pi I residue of this function 1 over z minus z1, z minus z2, evaluated at z sub question mark, whichever one it is, okay? Z sub 1 or z sub 2. In fact, why don't we just declare the one that's inside to be z sub 1 so I don't have some ambiguous statement like that. Z sub 1. And of course, simple pole, you just strike that one and evaluate the other one at that point, and it'll come out. And unless I made a mistake here, but I just did it myself, so that is a good problem. So anyway, that's a whole interesting class of problems, as was the other one. Okay, so we can do all manner of interesting integrals from minus infinity to plus infinity, but it's also possible to do completely different types of integrals around unit circles. And there are other clever contours as well. But we're going to leave it at these examples here. So 2 pi root a squared minus 1. If I'm wrong, let me know. Good, let's see how we're doing time-wise. We're doing fine. So we're going to call it good right now. This is the end, and we'll be in touch. Maybe we'll do a Zoom meeting or something. And let me know what you think in your emails. But until later, see you next time.